Here's one of my most favorite problems. Tim is in a boat 2 miles offshore, and his house is 5 miles down the beach. So it's 5 miles from his house to that point on the shore closest to the boat. So we know that he can row the boat at 3 miles an hour and walk at 5 miles an hour. So I'm going to write down that the rate that he can row the boat is 3 miles per hour, and the rate that he can walk is 5 miles per hour. And so what we have to determine is we want to minimize the time it takes to get home. Now, he has a choice to make. He can row his boat. The quickest he can get back to the shore is to row directly perpendicular to the shore right back to here, and then walk the remaining 5 miles to the house. Or he could row directly to the house. That's the shortest distance between the 2 points, is a straight line. It's the shortest distance, however, he rows his boat at a rate slower than he can walk. So we have to decide, okay, what is it better to do that? Or is it better to go directly to the shore and then walk because he can walk faster? Or would it be better if he went somewhere in between? And if so, where in between should he go? So we're going to pick a point somewhere in between. And it doesn't matter where I put it. I'm just going to put it right there. We have no idea what that is. So we're going to call that X miles downshore from the point directly offshore right here. We're going to go X miles toward the house and land the boat. And we need to figure out what's the optimal place to land that boat so its time is minimalized. So if we want to minimize time, we need a time equation. And so what is the time equation going to be? Well, we know the time that it takes to get home is going to be the time he takes in his boat plus the time it takes for him to walk. So how are we going to come up with those times? Well, you need to remember that rate times time is equal to distance. That's an old famous math formula. Rate times time equals distance. And time then would be distance divided by rate. So in order for me to come up with a time equation, I'm going to have to take the distance divided by the rate. Well, we were given the rates right here, but we don't know the times. And we don't really know the distances, although we know that this is 5 miles here, but we need to know the distance that he's going to travel in the boat and the distance he's going to travel in walking. So here's what we've got. We know that this value right here is x, and this value right here is 2. And because that's a right triangle, we know what the distance here that he's going to row his boat is in terms of x. And so we know, of course, that's going to be the Pythagorean theorem. So this will be the square root of x squared plus 4, because obviously x squared plus 2 squared equals hypotenuse squared. And of course, to take the square root of that, that's going to give me the distance in the boat. So we can write now that the distance in the boat is going to be the square root of x squared plus 4. And then the distance walking is going to be easily calculated because this whole thing is 5. We just took off x, and he's going to be here, and that's going to be 5 minus x. So this would be 5 minus x from where he lands the boat until he gets to his house. So that's the distance walking. And of course, time is distance divided by rate. And that's going to be, for the boat, the square root of x squared plus 4 over 3. And the time, and that's the time in the boat, the time walking is going to be 5 minus x divided by 5. And so my total time, and now I'm going to write it as a function of x, t of x, is going to be the time in the boat, which is the square root of x squared plus 4 over 3 plus the time walking, which is 5 minus x over 5. I'm going to rewrite the function so it's easier to take the derivative. So I will make that 1/3 times radical x squared plus 4. And then the last part, 5 over 5 is 1. And then negative x over 5 is negative 1/5 x. So now taking the derivative will be a lot easier. The first part is 1/3, a constant times the function, the square root, is going to be the derivative of the function, constant times the derivative of the function, 1 over 2 radical x squared plus 4, chain rule times 2x, plus the derivative of 1 is 0, and the derivative of negative 1/5 x is negative 1/5. So cleaning that up, t prime of x is going to be x on top. The 2's cancel. We got 3 times radical x squared plus 4 on the bottom, and then minus 1/5. We're going to set that derivative equal to 0 and solve to find our critical points. So we'll come up here and start a new column. If I take the negative 1/5 to the other side, we get 1/5 equal to x over 3 radical x squared plus 4. Cross products, 3 times radical x squared plus 4 is going to equal 5x. Square both sides. 9 times x squared plus 4 equals 25x squared. 9x squared plus 36 equals 25x squared. 36 equals 16x squared. X squared equals 36 over 16. And x will equal the square root of that, which is 6/4, or 3/2. So my critical point is x equals 3/2. We now need to determine, okay, is that a max? Is it a min? And we're going to actually use the candidates test here to do this because we do have endpoints. Our endpoints, our domain here for this problem is going to be x greater than or equal to 0 or less than or equal to 5. That's because x is the distance I'm going to land my boat down shore toward the house from the point directly directly offshore from where the boat is, right here. So x is the distance from there. Well, that distance, he could decide to row his boat directly to the shore, so x would be 0. Or he could row directly to the house, and so where he lands the boat is 5 miles downshore, so we have endpoints. So this is going to be an easy one to determine our max. So we're simply going to say, okay, we make a chart, and we have x and t of x. When x is the left end point 0, that one's an easy one. We plug that in. We will get 2/3 plus 1. So that's going to be 1 2/3, or 1.667 as a decimal. And when we plug in the critical point, 3/2, or 1.5, we get 1.533, and the 3's repeat. And then when we plug in the endpoint, x equals 5, we get 1.795. And all those, of course, are in hours. So we can easily see that our minimum time is going to be at our critical point. 1.533 hours will be the shortest time we can do it. So now we need to answer the question. And Tim should land his boat 1.5 miles down the shoreline from the point nearest the boat, which is directly, perpendicular, that right there, and also then walk the remaining 3.5 miles. And we do that. We say that last part just because you could land the boat 1.5 miles away from that point over here, which obviously would not minimize your time. So you need to be going, closest toward the house. So that is the problem. And again, this is the candidates test. First example we've done using that, and it's really nice because you don't have to do the first or second derivative test.